Hi friends, welcome to my channel. Let's have a look at problem 1020, number of enclaves. So in this video, we're going to share two formats of solutions based on traversal. So here, this problem requires to return the number of land cells in grid, for which we cannot walk off the boundary of the grid in any number of moves. So let's look at the examples here. So in example 1, so the return is 3. So the 3 cells depicted by pink are the cells satisfy the requirement of the problem. So this yellow one, actually, we can walk off the boundary. In example 2, so the return is 0 because all these 4 cells can lead to off the boundary. So the constraints on this problem are the following. So the number of rows and number of columns are bounded below by 1 and bounded above by 500. And the grid IG is either 0 or 1. So with that said, let's look at the method. So our method will be the standard traversal algorithms. So here the question is, how do we solve this problem? So first let's make a remark. So this problem is almost exactly the same as problem 1254, the number of closed islands. So the differences are the following. First is the return format. So we need to return the count of the number of required cells or desired cells. So in this problem. So in problem 1254, we are required to return the number of closed islands. So the second difference is that here 0 is representing the sea and 1 representing the land, and in problem 1254 it's the reverse. So here our plan is as follows. So we are going to provide two formats of solutions based on different thought processes. So first, we are going to use the identical code with Leetcode 1254 with a few tweaks, but we still give a line-by-line explanation here. And secondly, we traverse from the boundary land cells, and these cells lead to the sea. So that's not what we want. So then we count remaining inland 1 cells. So they are what we want to count. So with that said, we are ready to prepare the code. And here is a question. So because this is essentially finding connected components, or how many cells in the desired connected components. So can you write a solution using a disjoint set abstract data structure? In other words, the union find or disjoint set first. So with that said, let's look at our method 1. So this method, I'm going to use basically identical code with problem 1254. So for that, let me split into 3 parts. So first is the meta information. For this, I'm going to track the number of rows and number of columns. So that is length of the grid and the length of the grid 0. So that's it for this step. The second step is traversal hyperfunction. So I'm going to use depth first search here. So define DFS. So I'm going to start from a position which is going to be a land later. Then first I'm going to check if this connected component is a valid one. So valid means that it do not lead to off the boundary. So we initialize a visited site, which is the traversal. And also we want to use a container. So let me here actually, because we use depth first search, I'll directly use a stack. Then we are ready to do the while loop. So while s, first I'm going to pop from the head. The head of the stack will be the tail of the corresponding list. And then I'm going to add this position to the set. And then we want to check if this component can lead to the boundary of the boundary or not. So if r in 0 m minus 1 or c in 0 n minus 1. So this whole condition means that we are looking at a cell as a boundary. So if there is one which is in the boundary, so the whole connected component will lead to off boundary, right? So we're going to make it as false. So next we're going to traverse the 4 different neighbors. So for x, y in r minus 1c, r plus 1c, and r c minus 1 and r c plus 1. So we need to make sure this xy position is inbound, it's a land, and it's not visited. So this is standard. So if 0 less or equal than x less than m, and 0 less or equal than y less than n, and this is a land. So here land means the grid value is 1. And also we want to make sure we do not do repetitions, so not in visited. So if this is the case, then we're going to append this position to the stack. So that's it. And then we're going to return the valid flag and the visited set. So the valid tells us if it's corresponding to an inlet enclave, or in the language of problem 1254, a closed island. So the visited is the corresponding set representation for the connected components. So that's it for the hyperfunction. So thirdly, we're going to do the counting. So the difference of this problem from problem 1254 is that we're counting the all the valid cells, not the number of connected components satisfying the requirement in the problem. For that, let's initialize a count variable, and then we also initialize a set to avoid repetition in the traversal. Then we're going to do iterations, right, for I in range m, for j in range m. And then we are going to check if grid ij is land, and also ij not in visited. Then what we are going to do is we are going to do traversal, right, depth first search. So here is DFS, so ij. Then if valid, then we're going to add the number of cells in this current connected component to the count. So count plus equals length of s. And at the same time, no matter it's valid or not, so we're going to enlarge the set by union it with s. So that's it about the counting. And then we're going to return the count of the cells. So now let's do a special case check. It passes one special case. Now let's do a generic case check. Yeah, it passes the generic case. So first let's make a remark, and then we go to the next solution format. So here actually we borrow the identical code from Leetcode 1254, and the structure in this solution contains 3 parts. First part is meta information, and the second part is hyperfunction. In the hyperfunction, we introduced an extra flag variable if we compare with the vanilla traversal. And in the third part, it's basically a counting. And in this problem, what we count is not the number of valid connected components, rather we count the valid cells. So this is one solution. So because it's following the previous problem, so it's not very specific to this problem in some sense. And now let's call this problem, this solution, solution V1. Let's do another solution following our plan. So now what we are going to do is that, so we traverse from a boundary land. So this actually is will be more fast. The reason is that all connected components containing boundary lands, like here or here, so the cells in such connected components will lead to off the boundary. Therefore, they are not going to be count, right? So first we are going to change all this kind of land to be 0, and then we just count how many ones left in the grid. So that's the overall idea. So with that said, let's also divide this into several steps. First, meta information. So let's copy here this line. And next, we're going to write a hyperfunction. So this time in recursive format. So I'm going to call this function traversal, or just use some easy one. So let's call it traverse ij. So we can imagine this traversal function like a worker. Once he finds boundary ones or ones that connected to boundary ones, he will change the ones to be 0. And then after this work, we're going to count the ones remaining in the grid. So let's do this. So first, I'm going to check if 0 less or equal than I less than m at g. So not g. 0 less or equal than g less than m, and grid ig is 1. If this is the case, what we're going to do is that we're going to change the corresponding position to be 0. And then we look at the 4 neighbors. So for dx, let's see, di, dg in, so let's see, so 4 different increments. That's 1 and 0, 1, 0, -1. Then what we are going to do is that we traverse the neighbors. So that is I plus di, g plus dg. So that's it for this work. We do not need to return anything because we just we're going to modifying the grid itself. So that's the main hyperfunction. So next, so we traverse from the boundary lands. So if we found ones in boundary, so we just let the worker do the job. So that's actually very routine for I in range m. First, I'm going to check this first row and the last row. So we're going to traverse first column and last column, traverse I n-1. So notice that we do not need to check if the grid is 0 or 1, because if it's 0, so this guy does nothing. So once we traverse the first column and the last column, then we're going to check the first row and the last row. So then I'm going to use j in range. I'm going to start from 1, so then ending at n-1, but because these 2 corners are already visited, so I'm going to traverse, so 0 j and traverse m-1 j, right? So this way we let the work done all the jobs. So in other words, it changes all the cells connecting to the boundary cell with the cell being land to be 0. And then what we are going to do is that we just need to count how many ones left in the grid. That's the number of cells we need to return. So this is the routine. So we're going to return the sum. So the sum of each row, right, for row in grid. So that's it. So now let's do a special case check first. Yeah, it passes one special case. Now let's do a generic case check. Yeah, it passes the generic case. I guess for this video, it's about the end. So before we finish, let's make a remark. So we provided two formats of solution. Both solutions fall in the line of traversal algorithms. In the first solution, actually, we write a depth-first search function, and in between, we use a flag to check if the corresponding connected components contain the cells we're going to count or not. And then we do the counting afterwards. And also, in between, so we need to call the hyperfunction, and we use a visit set to avoid repetition. So that's the first solution. So this solution is inherited from problem 1254. And the second solution format actually slightly changed our thought process. So we're going to traverse from the boundary cells, and all the cells that are connected with the boundary cells, that being 1, are corresponding to the lengths that are not going to be counted in the final result. And after we let the worker do the job, then we just need to count how many ones are left in the grid, and that number is what we want to return. So with that said, I guess this problem provides us a good example for practicing traversal algorithms in different formats, like in recursive format or in iterative format. With that said, I guess that's it. Thank you very much.